somewhere on Earth tonight, a small flame is burning that no one lit, and no one knows how to put out. Before we go any further, if you want a brand new Earth topic every single night to fall asleep to, subscribe. One tap and a new story is waiting for you every evening. That flame might be flickering at the foot of a cliff in the woods of New York. It might be glowing in a crater in the deserts of Central Asia. It might be hissing softly behind a thin curtain of falling water, or rising from a crack in the side of a quiet Turkish mountain. These are the eternal flames of our planet, the fires that simply refuse to go out. Picture the Earth from high above, a slow blue-green sphere wrapped in soft white cloud. Most of it looks cool and calm. Vast oceans, wide forests, pale deserts moving under the wind. From up there, you would never guess that scattered across the continents are tiny, glowing points of fire that have been burning longer than any human alive. Some have been burning longer than any country. A few may have been burning longer than recorded history itself. Now drift closer. Imagine standing at the edge of a deep round pit in the middle of a flat brown desert. The ground around it is cracked and dry. Inside the pit, hundreds of small orange tongues of flame lick up from the earth day and night, in still air and in storms. The heat presses gently against your face. The light flickers across the sand, and it has been doing this without pause for decades. Now imagine a green hillside in Australia, where the grass is sparse and the rocks are warm to the touch. There is no visible fire here, only a faint wisp of smoke rising from the soil and a thin smell of sulfur in the air. Beneath your feet, deep inside the hill, a seam of coal has been smoldering for somewhere around 6,000 years. 6,000. It started before the first cities. It is still burning tonight. Picture a small cave in the woods of the eastern United States, tucked behind a curtain of falling water. A pale yellow flame burns there, sheltered from the spray, fed by a steady whisper of gas seeping out of the rock. Hikers crouch down and relight it when the wind blows it out. But the gas keeps coming. The flame keeps returning. And no one is entirely sure where, deep in the layered stone below, that gas is truly being made. This is the quiet wonder we want to sit with tonight. The simple, strange truth that fire, which seems so fragile, so easy to blow out with a single breath, can also be one of the most stubborn things on Earth. A campfire dies in a few hours. A house fire burns out in a day. A wildfire can roar across a forest for weeks. But these eternal flames work on a different clock entirely. They burn in decades, in centuries, in what might be thousands of years. And the central question, the one we will gently turn over and over as you drift off, is this: why? Why do some fires die quickly, while others find a way to feed themselves for lifetimes? What conditions, what hidden geometry of rock and gas and air lets a flame become, in a way, almost immortal? The answers are not as simple as you might think. Some of these fires are clearly natural, fed by gas rising from deep underground reservoirs. Others were started by accident, by a lightning strike, a coal car, a trash fire that crept into the wrong seam. A few were lit on purpose, in plans that did not go as expected. And for many of them, even after years of study, scientists still cannot fully agree on how they sustain themselves, how far they reach, or how long they will last. Some researchers believe these fires are slowly running out of fuel, dying inch by inch, year by year. Others suspect a few of them may have access to far more fuel than we realize, and could burn for many more human generations. The honest answer for most of these places is that we do not yet know. Tonight, we will travel from a desert crater in Turkmenistan to a smoldering mountain in Australia. We will visit a quiet ghost town in Pennsylvania, a cluster of mythic flames on a Turkish slope, and a cold, sleeping bog in the far north. We will sit beside each fire. We will listen, and we will let the mystery of how a flame can outlive an empire settle softly over us, like a warm blanket, as we begin to drift toward sleep. In the hills of New South Wales, in the southeastern part of Australia, there is a low ridge called Mount Wingen. The name is gentle and unassuming. From a distance, it looks like any of the soft, scrubby ridges that roll across that part of the country. Eucalyptus trees grow nearby. Kangaroos pass through in the early morning. The light has that pale, dusty quality you find in dry Australian bush. And yet, somewhere beneath the surface of this quiet hill, a fire has been burning for about 6,000 years. 6,000 years. That is older than the pyramids of Egypt, older than written language in most parts of the world. When this fire first flickered to life, much of humanity was still figuring out how to plant wheat. And it has been burning quietly ever since. This is the simplest way to describe Burning Mountain. It is a coal seam fire. Deep underground, a layer of coal is slowly, patiently combusting. The fire moves through the seam at the pace of about 1 meter each year. That is roughly the length of a walking stick, traveled in 12 full months. A snail would outpace it many times over. And yet, year after year, decade after decade, the fire continues to inch its way south through the ridge. The seam itself sits about 30 meters below the surface. Picture a 10-story building turned upside down and pressed into the earth. That is how far down the fire lies. You cannot see flames at Burning Mountain. There is no glowing crater, no roaring vent. What you see instead is the ground itself. The soil above the burn zone is warm to the touch. Steam rises in thin wisps after rain. The rocks have been baked into strange colors: reds, yellows, pale pinks, from centuries of slow heat. In some places, the surface has cracked open into small chimneys that breathe out warm, sulfurous air. The mountain is not actually a mountain in the way most people think of one. It rises only about 650 meters above sea level. That is about twice the height of the Eiffel Tower. By Australian standards, it is a modest hill. What makes it remarkable is not its size, but its temperature. The hottest patches of ground near the active burn can reach around 350 degrees Celsius. That is hotter than the inside of most home ovens at their highest setting. Yet it is all hidden, tucked away beneath a thin layer of earth and ash. How did it start? This is one of the small mysteries that surrounds the place. 6,000 years ago, something ignited that buried seam of coal. One theory is that a lightning strike traveled down into an exposed outcrop and lit the coal where it met the air. Another idea is that a bushfire reached a place where the seam came near the surface and slipped underground. Some researchers wonder if spontaneous combustion did the work. Coal can heat itself when it reacts with oxygen, and given enough time, it can quietly catch fire on its own. No one knows for certain which of these explanations is correct, and the truth may be something we cannot recover from such a distant past. The local Wanarua people knew of the burning ground long before European settlers arrived. Their oral traditions speak of the fire in the hill when a European stockman stumbled onto the smoking ridge in the early 1800s. He reportedly thought he had found a volcano. For decades, geologists agreed. It was only later that the truth became clear. There was no magma, no volcanic vent, no connection to the deeper heat of the planet, just coal and air and time. The fire feeds on a simple recipe. Coal provides fuel. Cracks and fissures in the rock above let in just enough oxygen. Heat builds slowly and travels through the seam. As one section burns out, the heat moves on to fresh coal further along. The ash and collapsed rock left behind seal the old burn zone, while a new front continues forward. In this way, the fire does not so much stay in one place as it walks, very slowly, through the earth. That is the basic picture. A buried fire, older than most human civilizations, moving at the pace of a child's footstep each year, hidden beneath a quiet ridge in a quiet country. And here is the part to hold gently as you drift off. We can describe burning mountain. We can measure it. But the larger question still hangs in the warm Australian air. How long can a fire like this last? How many more centuries will it walk southward through the coal? The answer remains open. Far out in the Karakum Desert, deep in the heart of Turkmenistan, there is a hole in the ground that has been burning for a very long time. The locals call it the door to hell, though its true name, Darvaza, simply means gateway. It sits in a flat, dry plain of pale sand and low scrub. By day, the desert wind rolls over the dunes in soft waves, and the crater looks like a wide bowl carved into the earth. By night, it glows. The orange light can be seen from miles away, flickering against the dark sky like a small, restless sun trapped in the sand. The crater is about 70 meters across and 20 meters deep. Inside it, hundreds of small flames lick up from the rocky floor. Some are no bigger than candle flames. Others rise in tall, twisting columns of fire. The walls are streaked with soot and pale minerals. The air above the pit shimmers with heat, and the smell of warm gas drifts on the wind. How did such a place come to exist? The story most often told begins in 1971. According to that account, a team of Soviet geologists was drilling for natural gas in the Karakum. They had set up their rig over what they believed was a rich pocket of methane buried beneath the sand. As they drilled, the ground gave way. A wide cavern collapsed under the weight of their equipment. The drilling rig fell in. The earth opened up, and from the new pit, a thick cloud of natural gas began to rise. The geologists, the story goes, were worried about the gas. Methane is invisible, but it can poison animals and people who breathe it in large amounts. They needed to stop it from spreading across the desert. So they made a decision that would shape the place for decades to come. They set the gas on fire. They believed the methane would burn off in a few days, maybe a few weeks. Then the flame would die, and the desert would be quiet again. That was over 50 years ago. The fire is still burning. That is the story most often repeated. But here is where the certainty begins to thin. The truth is, no official Soviet record of the event has ever been found. There are no clear documents, no detailed maps, no named geologists who stepped forward to claim the project. Some researchers who have studied the site believe the fire may have actually started later, perhaps in the 1980s. Others suggest that the crater itself may have formed earlier, and that the deliberate lighting was a separate event years after the collapse. A few have proposed that the methane was already seeping and burning naturally, and that the famous story of the lit match grew up around the site as a kind of legend. So the origin of the door to hell is itself a small mystery. We know the fire is real. We know the crater is real. We know natural gas is feeding the flames from below. But the exact moment it began, and the exact decision that lit it, sit just beyond the reach of clear history. What we do understand is the geology that made such a thing possible. The Karakum Desert lies above one of the largest natural gas reserves on Earth. Far beneath the sand, layers of ancient rock hold enormous pockets of methane, trapped there for millions of years. The rock above these pockets is sometimes thin and brittle. When something disturbs it, whether a drill, a shifting fault, or simply the slow weight of time, the ground can collapse. The gas finds a way up. If a spark finds it, the gas burns. This is the deeper origin of Darvaza. Long before any drill touched the sand, the conditions were already in place. A vast underground sea of methane, a thin ceiling of rock, a desert quiet enough that no one would notice a small collapse for a long time. The crater is, in a sense, only the visible part of something much older. The fuel beneath it has been gathering for ages. How long will the flames last? That, too, remains an open question. Early predictions gave the fire weeks. Later guesses gave it years. Now, more than half a century in, no one can say with confidence when the gas will finally run thin. Some believe the reservoir is so large it could burn for centuries more. Others think the flames may fade quietly in our lifetime, leaving only a warm, dark pit in the sand. For now, the door remains open, and the desert keeps its slow, glowing secret. Long before anyone wrote about coal seams or methane vents, people who lived near eternal flames wrote about them in other ways. They wrote prayers. They wrote myths. They built altars on the warm ground and gave the fires names. The flames that burned out of stone or earth seemed to belong to gods, or to spirits, or to forces older than memory. We sit tonight in a much later age, and we know a little more about what these fires are made of. But the wonder is still there, waiting under the science. A flame is a strange thing when you really look at it. It is not solid. It is not liquid. It is not quite a gas in the way the air around it is a gas. A flame is what happens when a fuel meets oxygen at a high enough heat, and the molecules break apart and rejoin in glowing patterns. The light you see is energy being released. The warmth on your face is the slow undoing of ancient sunlight stored inside the fuel. That phrase, ancient sunlight, is not a poet's flourish. It is a real description. The methane that feeds many eternal flames is built mostly of carbon and hydrogen. The carbon came from living things long ago. Plants pulled it out of the air using sunlight. Tiny ocean creatures pulled it out of seawater. When they died, they sank into mud and were buried. Heat and pressure cooked them slowly for millions of years. The sunlight they once drank is still locked inside the bonds between their atoms. When a flame finally releases it, you are watching very old light return to the world. The hydrogen in that methane has a stranger story still. Most of the hydrogen on Earth is older than Earth. It formed in the first few minutes after the beginning of the universe, when everything was hot and bright and simple. That hydrogen drifted through space for billions of years. Some of it gathered into the cloud that became our sun, our planet, and us. Every time a methane seep flickers in a Turkish hillside, some of that primordial hydrogen is finally taking part in a small, bright moment on the surface of a rocky world. The carbon has a different lineage. Carbon was forged inside stars. Old stars, much larger than our sun, fused lighter elements together in their hot cores. When those stars died, they scattered their carbon across space. That carbon eventually became forests and shellfish and coal and the gas that feeds an eternal flame. The fire you might sit beside in a quiet valley is, in a real sense, starlight finding its way back into the open. There are other ingredients too. Some seeps carry sulfur, which gives the flames a faint blue edge and a sharp smell. Some carry traces of helium, an element so light that most of it has already drifted away from Earth into space. The helium that lingers in deep rocks, formed from the slow decay of uranium and thorium over billions of years. When it escapes through a vent and joins a burning plume, it is taking its first and last breath of open air before rising forever. Water is part of the story as well. Even though water and fire seem like opposites, the hydrogen in water and the hydrogen in methane share the same deep history. And some researchers suspect that much of Earth's water arrived on comets and icy bodies during the planet's early years. If that idea is right, then the oceans, the rain, even the moisture inside the fuel of a slow-burning peat fire all share a kinship with frozen visitors from the outer reaches of our solar system. Other researchers think most of the water was here from the start, locked inside the rocks that built the planet. The question is not fully settled. Stone matters too. The eternal flames almost always burn near certain kinds of rock. Limestone, shale, sandstone, and coal beds shape how gases travel underground. The minerals inside these stones formed from older mountains, older seas, older lives. When a vent finally opens at the surface, the path the gas took through the rock can be older than any human civilization that ever knelt beside the flame. Sacred texts from many cultures speak of fires that never died. We cannot always know which specific places those writers meant. Some scholars believe certain ancient temples were built around natural gas vents. Others think the descriptions are symbolic. The link between real eternal flames and the fires written about long ago remains a soft, open question, glowing quietly in the space between geology and human memory. Far below the surface of the earth, in the dark seams of buried coal, a slow and patient fire can wake up and never go back to sleep. To understand how that happens, picture what coal actually is. Coal began as ancient plants, packed down over millions of years, pressed by the weight of rock above. Inside that black stone is carbon, and carbon loves to combine with oxygen. When the two meet under the right conditions, heat is released. That heat, given time, can build into a quiet, hidden flame. The strange thing is how little it takes to start one. A coal seam does not need a lightning strike or a careless spark. It can begin to warm itself. This slow warming is called oxidation, and it works like a very lazy fire. Air seeps through cracks in the rock. The oxygen brushes against the coal. A tiny amount of heat appears. If that heat cannot escape, it gathers. Slowly, the coal gets warmer. Warmer coal reacts faster. Faster reactions make more heat. And so, the seam begins to climb toward ignition, sometimes over months, sometimes over years. This is the first invisible force at work, the gentle pull of chemistry multiplied by patience. No one sees it. No one hears it. Deep in the seam, the temperature creeps up by a fraction of a degree, then another, then another. By the time anyone notices, the rock above has grown warm to the touch, and a thin curl of smoke is drifting from a crack in the ground. The second force is pressure. The earth is heavy. Every layer of rock presses down on the one beneath it. In a deep coal seam, that pressure squeezes the coal, the surrounding stone, and the pockets of gas trapped inside. When a fire begins below, the heated gases try to expand. They push outward, looking for any small path to the surface. Pressure helps them find it. Cracks widen. Old mine shafts become chimneys. Fresh air rushes in from one opening, and hot gas rises out of another. The fire breathes through the earth itself. This breathing is the third force, and it may be the most important of all. A coal seam fire cannot live without air, but it also cannot live if the air moves too quickly, because then the heat would be carried away. The flame needs a slow, steady draft, like an old fireplace with the damper half closed. Inside a buried seam, the rocks and tunnels create exactly that kind of draft. Cool air sinks in through fissures. Warm air rises out through vents. The system balances itself, sometimes for 100 years or more. Some researchers wonder if certain seams have shaped their own airflow over time, opening and closing pathways as the rock around them shifts. Others think the airflow is simply a happy accident of geology. The question is still open. Heat itself is the fourth quiet force. Rock is a poor conductor of warmth. That means heat travels slowly through stone, like honey through cloth. In an open fire, heat escapes into the sky. In a buried seam, heat has nowhere to go. It builds up in the surrounding rock, baking it, drying it, cracking it. The hotter the rock becomes, the easier it is for the fire to keep moving forward into fresh coal. The fire becomes its own architect, preparing the path ahead. Then there is gravity. As coal burns, it leaves behind ash and empty space. The ground above loses its support. Over time, sections of earth can sag and sink, forming long depressions or sudden pits. These collapses change the way air moves through the seam. Sometimes they smother part of the fire. Sometimes they feed it a great gulp of fresh oxygen and send the flames racing in a new direction. No one can predict exactly how a collapsing roof will steer a fire below. All of these forces, chemistry, pressure, breathing, heat, and gravity, work together in ways that are still not fully understood. Engineers can model parts of it. They can map the heat with sensors and trace the gases at the surface. But the deeper parts of a seam fire remain hidden. We can listen to it. We can measure what comes out. We cannot quite see what it is doing in the dark. That is part of why these fires last so long. They are tended by forces older and slower than us. They feed on a fuel laid down before any human walked the earth, and they burn on a clock that does not care about our lifetimes. Somewhere tonight, in a seam far below a quiet field, a small warm patch is growing just a little warmer. No one knows yet whether it will ever rise to the light. In the gentle hills of eastern Pennsylvania, there is a place where the ground itself has been warm for more than 60 years. The town is called Centralia. Once, it was home to more than 1,000 people. Now, only a small handful remain. The streets are still there mostly, though the forest has begun to take them back. And underneath those quiet streets, deep in the rock, a fire has been burning since 1962. To picture the size of this fire, imagine a slow river of heat creeping through tunnels of coal. The fire is not a single flame you could point to. It is a vast underground burn, spread across an area that has grown to cover roughly 400 acres. 400 acres is about the size of 300 soccer fields laid side by side. All of that smoldering quietly under the soil for longer than most adults alive today have been on Earth. The temperatures down there are hard to imagine. In the hottest pockets, the rock is thought to reach around 1,000 degrees Fahrenheit. That is about 5 times hotter than boiling water. It is hot enough to soften steel. And yet, on the surface, you might only feel a gentle warmth rising from a crack in the road. You might see a thin curl of steam drifting up on a cold morning, the way breath drifts from a sleeping animal. The scale of the fire is hidden by the calm of the surface. Geologists have tried to measure how deep the burn reaches. Some estimates place the active fire layers around 300 feet below ground, roughly the height of a 30-story building. Others suggest the fire has crept even deeper in places, following the slanted veins of coal that snake through the bedrock. The exact shape of the burn is still not fully known. The ground hides its secrets. Mapping a fire you cannot see in tunnels you cannot enter is a slow and uncertain task. How much coal has burned in those 60-some years? No one is entirely sure. One commonly cited figure suggests the fire could keep going for another 250 years before it runs out of fuel. Another estimate stretches that timeline closer to 1,000 years. The difference between those two numbers is enormous. It is the difference between a fire your great-grandchildren might see end and a fire that will outlast every nation currently on a map. The truth depends on the size of the coal seam, the flow of air through the cracks, and the strange chemistry happening in places no human can reach. To put that in perspective, think about how long a candle burns. A simple household candle might give you 8 or 10 hours of light. A large bonfire, fed all night, burns for perhaps 12. A forest fire, even a huge one, usually exhausts itself within weeks or months. Centralia has been burning for over 22,000 days. If each of those days were a single page in a book, the book would be thicker than most novels on a shelf. And the fire is still on the first chapter by some measurements. The reasons it burns so slowly are part of the open question. A coal seam fire does not roar. It breathes. Air seeps in through tiny fractures in the rock, just enough to keep the embers glowing, but not enough to let them flare. Some researchers think the fire feeds itself through a quiet rhythm, drawing in cool air through one set of cracks, releasing hot gases through another, almost like a lung. Others wonder if the slow burn is more chaotic than that, with pockets going dim for years, and then reawakening when fresh oxygen finds them. The mechanism is still debated. Engineers have tried on and off for decades to stop it. They have dug trenches. They have flooded sections with water and clay. They have tried to cut the fire off from its fuel by removing the coal ahead of it. none of these efforts has worked for long. The fire keeps finding new pathways. Some experts now believe that putting it out would cost more than the entire town was ever worth, and that the only practical choice is to let it burn itself to sleep across the coming centuries. The scale of Centralia is not just measured in acres or degrees. It is measured in human time. A child born when the fire began is now approaching old age. The fire has outlasted careers, marriages, elections, and entire industries, and still it burns quietly beneath the green hills, holding a question that none of us will live long enough to answer. How long, in the end, can a fire feed itself? Centralia is still working on the reply. Imagine standing on a quiet hillside at dusk, somewhere along the edge of a wide green valley. The light is fading. The grass is damp under your feet. At first, you see nothing unusual. Then, near a low patch of mossy ground, you notice a small flicker. A soft blue tongue of flame, no bigger than a candle, dancing just above the soil. It makes no sound. It casts almost no light. It simply burns there, fed by something rising up from far below. These small flames appear in many places around the world, and they are often called methane seeps. Methane is a gas. It has no color and almost no smell on its own. It forms deep underground, sometimes from old plant matter pressed into coal or shale, and sometimes from tiny living things that break down buried material in the dark. The gas is lighter than the rocks above it, so it drifts slowly upward year after year until it finds a crack and slips out into the open air. When that gas meets a spark, or a hot surface, or even just the right mix of oxygen, it can catch fire. And because the supply from below is steady, the fire can keep going for a very long time. Some of these little flames have been burning for centuries. Others come and go, flickering for a few seasons, and then quietly fading as the gas finds a new path. The surface around a methane seep often has a strange, gentle character. The ground may look perfectly ordinary at first glance. Soft grass, a scattering of stones, a few patches of low shrub. But step closer, and the details begin to whisper. there might be a small patch of bare earth where nothing grows, baked dry by warmth from below. The soil may take on a pale, almost ashen color. Around the edges, the moss can look thicker and greener than elsewhere, fed by the warmth and humidity that the seep gives off. In some places, the gas does not light itself. It simply rises, invisible, and you would never know it was there unless you held a flame near the ground. Researchers sometimes do exactly that, walking slowly across a hillside with a small torch, watching for the moment when the air seems to ignite in their hand. A blue glow appears. They mark the spot. They move on. In other places, the seep has been burning for as long as anyone remembers. Local people may have given it a name. They may have built a small ring of stones around it, or left offerings nearby, or simply walked past it without comment for generations. The flame becomes part of the landscape, like a tree or a spring. It is just there. What makes these seeps so curious is how little we truly know about them. We can guess where the gas comes from. We can sometimes trace it back to a layer of coal, or a pocket of shale, or a slow biological process in the deep soil. But the exact path the gas takes from its source to the surface is often hidden. It may travel through cracks too small to map. It may pool in chambers we have never seen. It may shift its route over the centuries as the rocks above settle and move. One theory is that many small methane flames are fed by ancient coal beds, slowly leaking their gas through fractures shaped by long ago earthquakes. Another idea is that some of these seeps are fed by living microbes, working in the dark, producing fresh methane year after year. Both theories may be true in different places. We cannot always tell which is which without drilling, and drilling can disturb the very thing we want to study. Floating above one of these landscapes in your imagination, you might see a patchwork of soft greens and browns, broken here and there by tiny pale rings where the warmth of the seep has shaped the soil. At night, if you knew where to look, you might see a faint blue glimmer near a stone, almost too soft to be sure of. You would have to stand very still. You would have to let your eyes adjust. The flames are humble. They do not roar or rage. They simply continue. And the gas continues to rise, drawn by forces we still do not fully understand. From depths we have only begun to map. How long any one of these small fires has been burning, and how long it will keep burning, are questions no one can answer with certainty. They are quiet mysteries. They sit on hillsides and beside streams, glowing softly in the dusk, asking nothing of anyone who passes by. In a quiet corner of western New York, deep inside a small park called Chestnut Ridge, there is a waterfall with a secret tucked behind its falling water. The stream is gentle. The rocks are coated in moss and old leaves, and behind the thin sheet of water, in a small hollow worn into the shale, a tiny flame flickers. It is no bigger than the flame of a candle, but it has been burning on and off for as long as anyone can remember. Hikers walk up to the falls and lean in close. They cup their hands around the little glow to keep the spray from putting it out. Sometimes the flame goes dark. A passing breeze, a heavy drip, a careless boot. But the gas keeps seeping from the rock, and someone always relights it. The flame returns. It has returned for at least 200 years that we know of, and likely much longer than that. What makes this little fire so strange is what lies beneath it. To understand the flame, you have to think about what is happening far below your feet. The shale here is part of a much larger formation, a thick bed of dark, layered rock that stretches across a wide region. Inside that shale, locked into the tight black layers, there is gas, mostly methane, some ethane, some propane, some heavier cousins. The gas was made long ago, when ancient mud full of dead plants and tiny sea creatures was pressed down and slowly cooked over millions of years. In most places, shale this shallow should not give up its gas easily. The deep shales that energy companies drill for gas sit thousands of feet below the surface, where heat and pressure are high. The shale behind the waterfall is close to the surface, cooler, and not nearly hot enough to be making fresh gas right now. Yet gas still seeps out day after day, year after year, with no sign of slowing. That is the quiet puzzle of the eternal flame falls. The textbook answer says the rock here should not be warm enough to keep producing methane. But it does. Researchers who studied the seep found that the surrounding shale stays cool. Something is feeding the flame, and the simple story does not quite fit. One idea is that the gas is leaking up from a deeper, warmer layer through tiny cracks in the rock. The shale beds tilt and bend underground. Fractures run through them like fine cobwebs. Gas made in a hotter zone far below could drift slowly upward along these hidden paths, gathering in a small pocket behind the waterfall before whispering out into the air. By this view, the seep is a small chimney for a much larger system. Another idea is that the gas is being made right there in the shallow shale, but by chemical pathways we do not fully understand. Perhaps certain minerals in the rock help break down ancient organic matter at lower temperatures than expected. Perhaps tiny microbes in the deep cracks are quietly nibbling at the carbon and giving off methane as a byproduct. Or perhaps it is some mix of all these things at once. The honest answer is that the seep does not match what we thought we knew, and the research is still ongoing. Stand close to the falls, and you can almost picture it. The cold spray on your face, the hush of water on stone, the faint orange flicker, no taller than a thumb, dancing inside the wet hollow. And below you, layer upon layer of dark shale, holding its old breath, releasing it one slow molecule at a time. The flame above is only the visible tip of a long, slow process happening in the rock. There are other seeps like this scattered around the world, behind cliffs, inside caves, along the banks of quiet creeks. Many are small. Many were known to local people long before any scientist came to measure them. They were lit by lightning, by lanterns, by curious travelers who held a match to a strange smell rising from the ground. Some have lasted, some have faded. Nobody can say for sure why one seep burns for centuries, while another goes out in a year. The depth of the mystery is part of its charm. Far beneath the moss and the falling water, beneath the shale and the buried streams, gas is gathering and rising in ways we have only begun to map. The little flame behind the waterfall is a doorway, in a sense, a small bright window into a hidden world of slow chemistry and old rock. For tonight, let it stay a small flame, quiet, patient, fed by something we do not fully see, and still somehow burning on. Far in the north, where the land turns soft and wet, there are fires that no one can see. They live underground, deep inside the peat. Peat is a thick, spongy soil made from plants that died long ago and never fully rotted away. In cold, wet places, dead moss and roots pile up for thousands of years. Slowly, they squeeze together into a dark brown fuel. It looks like soil. It smells like earth. But when it dries out, it burns. These fires have a rhythm, like the slow breathing of the land itself. They wake in the warm months when the sun pulls moisture from the top layer of the bog. A lightning strike, a careless spark, or even the heat of a sunny day can light the surface. Then the fire sinks. It slips down through the cracks and roots into the dry pockets below. Once it gets there, it begins a long, quiet meal. It eats the peat the way a candle eats a wick, glowing red without flame. Up above, summer ends. The first snow falls. The world looks frozen and still. Yet under the white blanket, the fire keeps eating. Peat insulates itself. The thick, wet layer on top traps the heat below. Snow can pile a meter deep, and still, far underneath, the embers hold their warmth. Some peat fires have burned through entire winters and come back in spring, smoke curling out of the melting snow like breath from a sleeping animal. This is the strange cycle of the northern burn. Wet season, dry season, freeze, thaw. Each turn of the year gives the fire a new chance to spread or to sleep. In wet summers, the rain may soak the upper peat and slow the smolder. In dry summers, the fire reaches sideways, finding fresh fuel in every direction. It can creep for months at the pace of a slow walk, then pause for years, then wake again when conditions shift. How long can one of these fires live? Researchers are still trying to answer that. Some peat fires in Indonesia and Siberia have been tracked for decades, flaring and resting in waves. Others may be much older than the records that describe them. In 2020, scientists studying the Arctic noticed something curious. After unusually warm summers, smoke rose from places that had burned the year before. The fires had not died. They had simply gone underground, waited out the cold, and returned with the warmth. People began calling them zombie fires because they seemed to rise from the dead. One idea is that these zombie fires survive in deep pockets of dry peat, sheltered from snowmelt by layers of frozen ground. Another idea is that some of them are not truly continuous, but rather new fires lit by hidden hot spots left behind from the year before. The truth may be a mix of both, and the line between the two is hard to draw. The peat is dark, the ground is thick. No one can watch a single ember through a whole winter. There is a deeper rhythm at work, too. Peat takes thousands of years to form. A meter of peat may hold 10,000 years of slow growth. When it burns, the fire releases that long, patient archive of plants back into the air. Carbon that was locked away during the last ice age can rise as smoke in a single season. The bog breathes out what it spent millennia breathing in. Whether this exchange is part of a natural long cycle or something now pushed out of balance is one of the open questions of modern climate science. The visible signs are gentle and easy to miss. A patch of moss that looks slightly browner than the rest. A thin column of steam in the cold morning. A soft warmth under your boot when the surrounding ground is freezing. Reindeer have been seen lying on these warm spots in winter, resting on the heat of a hidden fire below. The animals do not know what burns beneath them. They only know it is a quiet place to sleep. How long can a single peat fire feed itself? Some may last a season. Some may last a century. Some may already have been burning before anyone in the region kept records of such things. The cycle continues whether anyone watches or not. Snow falls. Snow melts. The smoke returns. The land breathes slow and deep in a rhythm older than any village, older than any name on a map. Beneath the soft green moss of the far north, somewhere, right now, a small red glow is eating its way through ancient plants, keeping a fire alive that may outlive everyone who ever wondered about it. On the southern coast of Turkey, in a quiet stretch of pine forest above the Mediterranean, small flames flicker from cracks in the bare rock. They have been burning for as long as anyone can remember. The place is called Yanartas, which means flaming stone. The local people climb a stone path through the trees at dusk, and at the top, they find dozens of little fires dancing on the open hillside. Some are no bigger than a candle. Others rise to the height of a child. These flames are part of a wider neighborhood of fire. They do not stand alone. All along this coast, the land leaks gas. The gas seeps up through faults in the rock, mixes with the air, and burns wherever a spark or an old flame happens to meet it. The fires here are old neighbors of older fires. People have tended to them, told stories about them, and warmed their hands beside them for thousands of years. The ancient Greeks knew this hillside well. They believed it was the lair of a creature called the Chimaera, a beast made of 3 animals stitched together, breathing fire from deep inside the mountain. Sailors used the glow of these flames as a kind of natural lighthouse, steering their wooden ships toward the coast in the dark. The fires were a landmark, a meeting place, and a mystery all at once. The myth gave the seeps a name that science still uses today. Geologists call gas that burns at the surface like this a chimera, after the creature in the story. What makes the Yanartas flames unusual is what feeds them. Most natural gas seeps on Earth release methane, which is created by buried plants and animals breaking down over millions of years. The gas at Yanartas does contain methane, but it also contains hydrogen, and that is where the puzzle begins. Hydrogen is rare in surface gas seeps. It usually does not last long in the open air. So where does this hydrogen come from? And how is it being made fresh day after day, century after century? One leading theory points to a slow chemical reaction deep in the rock below. The mountains here contain a kind of stone called serpentinite, which forms when seawater works its way into iron-rich rock far underground. As the water meets the iron, it can release hydrogen gas. This process is called serpentinization, and it is thought to happen quietly over enormous spans of time. If this is the source, the fires of Yanartas are being fed by chemistry happening kilometers below the listener's feet. Another idea suggests the hydrogen comes from a more ordinary mix of buried gas and broken organic matter. With the unusual blend, explained by the strange path the gas takes through fractured rock. The two ideas are not entirely separate. Both could be partly true. Researchers still debate which process matters most and how much fuel is really down there. The question of how long these flames can keep burning depends on the answer, and the answer is not yet clear. The neighbors of these fires include other gentle wonders. Just up the coast, mud volcanoes bubble slowly, pushing cool gray paste to the surface, along with little hisses of gas. Out at sea, methane seeps rise from the floor of the Mediterranean, where strange communities of clams and bacteria gather around the trickles of food. Inland, hot springs warm the rocks where Roman bathers once soaked. All of these features share something. They are places where the deep earth is leaking, gently and steadily, into the world we can see. The Yanartas, flames sit inside this network of seeps and springs, like one bright knot in a long, slow of breathing rock. When one flame is smothered by wind or rain, it often relights itself within minutes from a nearby flame or from a fresh wisp of gas finding a warm stone. The fires move slightly over the years. New cracks open. Old cracks quiet down. The hillside is alive in a way that has nothing to do with plants or animals. How long can this go on? No one knows. The reservoir of gas could last another 1,000 years, or another 100,000. Or it could fade within a few human lifetimes if the supply runs thin. The myth of the Chimaera imagined the fires as the breath of a single beast that could one day be slain. The science imagines something stranger and slower. A whole region of stone quietly exhaling. A coastline of small flames keeping each other company in the dark, while the listener pictures the old stone path winding up through the pines and the soft orange glow waiting at the top. In the far north, the ground itself holds a secret. Beneath the tundra of Siberia, Alaska, and northern Canada, a layer of frozen earth stretches downward for hundreds of meters. This is permafrost soil that has stayed below freezing for at least 2 years, and often for tens of thousands. It is one of the coldest places on the surface of the earth, a vast underground vault of ice and frozen mud. And yet, somewhere inside this frozen vault, fire has learned to live. That seems impossible at first. How can a place that is frozen solid also burn? The answer lies in what the permafrost contains. Locked inside the ice are huge amounts of ancient plant matter, peat, methane, and pockets of natural gas. When the surface thaws, even a little, that fuel becomes available. And once a fire finds its way in, the cold around it does not always put it out. Sometimes the cold simply slows it down, letting it smolder for years beneath the snow. These are called zombie fires, and they may be the strangest burning places on Earth. A wildfire sweeps across the tundra in summer. The flames seem to die when autumn arrives. Snow falls. The land turns white and silent. But deep below the surface, in pockets of dry peat insulated by frozen soil, embers keep glowing. They breathe in trickles of oxygen through cracks in the earth. They feed on roots and old moss compressed into fuel over thousands of years. When spring returns, the snow melts and the same fire rises again, sometimes kilometers from where it first appeared. The extremes here are hard to picture. Some of these underground fires have been measured burning at temperatures hot enough to melt metal, while the soil only a meter away remains frozen hard as stone. The contrast is almost unreal. A single landscape can hold both the deep chill of an ice age and the slow heat of a furnace, separated only by a thin sheet of frozen mud. The oldest of these fires may be far older than anyone first guessed. Researchers studying scorched layers in Arctic peat have found burn marks going back centuries. Some of these layers seem to record the same fire returning again and again, as if a single ember had outlived generations of human beings above it. Whether one continuous fire can truly survive that long, or whether new fires simply find the same fuel each time, is one of the open questions of this strange landscape. One idea is that the cold itself acts as a lid, trapping just enough heat to keep an ember alive through the long polar winter. Another view is that the fires die fully each year, and only the conditions repeat. The evidence is incomplete, and the ground is too vast to check. The scale is the most quietly astonishing part. In some recent Arctic summers, satellite cameras have spotted hundreds of these underground hotspots glowing at once across Siberia and northern Canada. From above, the tundra looks calm and green, but the thermal images show a scatter of warm dots, like coals in a fireplace seen through gray ash. Each dot is a small fire chewing slowly through peat that has been frozen since the last ice age. The fuel down there is thought to be enormous, possibly more carbon than all the world's forests combined. How much of it is reachable by these slow fires, no one yet knows. The deepest of these smolders may travel meters below the surface, following seams of dry peat, the way water follows a stream. They can move sideways without ever breaking the surface, leaving the grass and moss above them untouched. A reindeer could walk across the warm ground and feel nothing strange. Then, weeks later, a small patch of soil might collapse, revealing a glowing hollow underneath. The fire has been there all along, quietly turning ancient plants into smoke. What makes the permafrost fires feel most extreme is their patience. A forest fire burns in hours. A grass fire moves in minutes. These hidden fires can take a decade to cross a single hillside. They burn at their own slow pace, indifferent to seasons, indifferent to weather, almost indifferent to the cold around them. Some researchers wonder whether a single zombie fire could, in theory, smolder for 100 years if the fuel and the airflow held steady. Others suspect they all eventually starve out and only seem continuous. The question of how long one of these quiet northern fires can truly live remains open, hidden somewhere beneath the snow, waiting for the next thaw to reveal a little more of its long, patient story. Beneath the soft grass of city parks, beneath the cracked asphalt of forgotten lots, there are places that smolder without anyone noticing. They are the old landfills, the buried mounds where decades of household refuse were laid down and then quietly covered over. Most of these places sleep peacefully. A few of them burn, and the burning is so slow, so deep, so hidden, that it can continue for years before anyone realizes the ground itself has caught fire. These are not the bright flames you might picture. There are no roaring tongues of orange, no crackling logs. A landfill fire is more like a whisper. It moves through compacted layers of paper, wood, plastic, and food waste at a creeping pace. The temperature rises gently, then sits there, holding itself just hot enough to keep going. Researchers sometimes describe it as a fire that breathes through pinholes, tiny openings in the soil let in just enough air. Tiny vents let out just enough smoke. The fire never quite has a feast, but it never quite starves either. What scientists find quietly beautiful about these fires is how strange the chemistry can be. Down inside the buried garbage, oxygen is scarce. So the fire is not really a fire in the way we usually think of one. It is closer to a slow roasting. Engineers call this smoldering combustion, a kind of burning that creeps along surfaces instead of leaping into the air. The temperature inside can sit between 200 and 600 degrees Celsius for years. No flame, no light, just hot, dark layers slowly turning to ash deep below the surface. The smoke that drifts up tells its own quiet story. It is often pale, sometimes blue-tinged, sometimes nearly invisible in daylight. On a cold morning, you might see it rising from a crack in the soil like the breath of some sleeping animal. Researchers who study these sites talk about walking across a meadow in winter and noticing that the frost has melted in odd, curving patterns. Those patterns trace the fire underneath. The ground above stays green a little longer in autumn. Snow vanishes from one patch of hillside while the rest stays white. The fire reveals itself by what it touches gently from below. Why some old landfills catch fire and others do not is a question that still puzzles engineers. One idea is that certain mixtures of waste generate heat on their own as they decompose. Bacteria break down organic matter and release warmth. If the pile is just dense enough, the heat cannot escape, and the temperature climbs until something deep inside ignites. Another idea points to outside sources. A buried ember from a surface fire, a discarded battery slowly shorting out, a chemical reaction between damp metals. The truth in any single case is often impossible to pin down. By the time the fire is found, the the evidence has long since burned away. The slowness is what gives these fires their strange character. A forest fire is loud and fast and done. A landfill fire might smolder through 5 winters and 6 summers without changing much at all. Workers who have studied them describe the way the smell shifts with the seasons. In warm weather, the smoke carries a sharp, acidic note. In the cold, it turns sweeter, almost like damp wood. The fire itself does not care about the calendar. It simply continues, eating slowly through whatever was buried decades ago by people who are no longer alive to remember. Putting one out is its own quiet puzzle. You cannot pour water on a fire you cannot see, not really. Water poured onto the surface mostly runs off or pools above the heat. To reach the burning layers, crews sometimes drill long shafts down into the mound and pump in inert gases or wet clay slurries. Other times they dig the burning material out, piece by piece, exposing it to the air and letting it cool. Both methods take months, sometimes years, and there is always the worry that the fire will simply move sideways, escaping into a cooler corner of the pile and resuming its slow life there. What remains open is just how many of these hidden fires are burning right now. Beneath the quiet edges of towns no one thinks much about. Estimates exist, but estimates are not the same as knowing. Some sites smolder unnoticed because no one is watching. Some have probably gone out on their own, starved by rain or chemistry. The fires below our forgotten landfills keep their own counsel. They burn the slow, patient burn of things that nobody invited, nobody planned, and nobody quite understands. There are lakes on Earth that seem to hold a slow fire inside them. Not flames in the way we usually picture flames, but a deep glow that rises from the water at night. The lava lakes of certain volcanoes do this. They rest in the open mouths of mountains, and after the sun goes down, they breathe out a soft orange light that paints the clouds above. For most of human history, no one knew quite what to make of them. The earliest written accounts come from sailors. Long ago, ships passing distant coastlines would see a faint red bloom above a peak in the dark. The crews wrote about it in their logs, sometimes with awe, sometimes with worry. They had no word for a lake of molten rock. They called it a beacon, a torch, a fire on the mountain. Some thought a great forge burned inside the stone. Others thought a hidden village kept its hearths lit through the night. The first careful descriptions came from explorers who climbed close enough to look. They reached the rims of these craters with rope, with mules, with simple wool coats against the cold. What they saw at the edge was hard to describe in a letter home. A pool of liquid stone, sometimes the size of a small pond, sometimes wider than a town square. Its surface was dark and crusted like burnt bread. Through cracks in that crust, a brighter glow shifted and pulsed. For a long time, no one could agree on what fueled it. One early idea was that the heat came from coal burning deep below the mountain. Another idea was that the rock itself caught fire, as if stone could be tinder. A third idea suggested that water meeting some hidden chemical produced the heat. These guesses were not foolish. They were the best minds of their time, working with the tools they had. The truth that the heat came from the deep interior of the planet itself was still beyond reach. The instruments they built to study these lakes were simple at first. A thermometer on a long pole, a bucket on a chain, lowered carefully toward the edge of the crust. Some early researchers tried to scoop a sample of the molten rock and pull it up to study. The chains melted. The buckets warped. Pieces of cooled lava came back as black glass, light and sharp, and these were carried home in wooden boxes. Scientists in distant cities held the dark fragments and tried to read them like letters from another world. By the middle of the 19th century, better tools arrived. Pyrometers, which measure very high temperatures from a safe distance, gave the first true readings. The lava lakes were close to 1,000 degrees Celsius at the surface and hotter still below. Spectroscopes, which split light into its colors, revealed the gases rising from the lakes. Carbon dioxide, sulfur dioxide, water vapor. The mountains were exhaling the breath of the planet's interior, and the glow was simply hot rock cooling and reheating in a slow churn. Even with these discoveries, the deeper question stayed open. Why did some lava lakes persist for decades or centuries, while others closed over and went quiet within a year. Two main ideas grew up around this puzzle. One held that a lasting lake needed a steady pipe of fresh magma rising from far below, like a slow chimney that never stops drawing. The other held that the lake recycled its own material, with cooled crust sinking, melting again, and rising once more in a closed loop. Both ideas had evidence. Neither fully explained every case. The mountains in question are well known to geologists. Erta Ale in the African Rift, Mount Erebus on a southern continent, near Ragango in Central Africa. Each has been watched and measured for many years. Each still surprises the people who watch it. A lake can shrink for a season and then rise. It can drain entirely and then refill. The clockwork is real, but the clock keeps its own time. The history of discovery here is really a history of admitting how little we knew. Sailors saw a light and named it wrong. Explorers climbed close and guessed wrong. Each generation built better instruments and learned that the answer was bigger than the question they had asked. The lava lake was not a fire in the old sense. It was a window into something much deeper, a slow conversation between the surface and the core, written in heat and light. And so we still stand at the rim, in a way. We know more than the sailors did. We know less than we wish. The glow rises into the night air, and the mountain breathes, and the old question waits. Far up in the Canadian Arctic, along the lonely shore of the Beaufort Sea, there is a stretch of coastline that has been burning for longer than anyone can remember. They are called the Smoking Hills. From a distance, they look like ordinary cliffs, brown and gray, and folded against a cold sky. But thin plumes of white smoke drift up from their slopes, day after day, year after year, in a place where almost nothing else stirs. The first European explorers who passed by these cliffs in the 1800s thought they were looking at signs of human settlement. They steered closer, hoping for warmth, and found only empty stone and steam rising from the rocks. The fire inside the Smoking Hills is not driven by coal in the usual sense. The cliffs hold layers of oil shale rich in a mineral called pyrite, sometimes nicknamed fool's gold. when the sea slowly wears away the cliff face, fresh pyrite is exposed to air for the first time in millions of years. The pyrite reacts with oxygen, heats up, and eventually ignites the oily rock around it. The hills, in a sense, light themselves. No lightning strike is needed. No human spark. The air itself is the match. That alone is strange enough. But the smoke that rises from these cliffs is more unusual still. It carries sulfur compounds so strong that the soil downwind has become startlingly acidic. Small ponds near the hills have a pH closer to lemon juice than to ordinary lake water. Plants that grow elsewhere in the tundra cannot survive there. The fire is not only burning the rock, it is reshaping the chemistry of the land around it, quietly and without rush, across a span of centuries. Scientists are not entirely sure when the smoking hills first ignited. Some estimates suggest the fires have been active for hundreds of years. Others wonder if certain pockets have been burning in slow rotation for thousands. As one stretch of cliff is consumed and falls into the sea, another stretch is exposed, and the fire moves on. The flames are not the same flames century after century. They are more like a wandering ember, walking slowly along the coastline as the shoreline itself retreats. Far away, on the other side of the world, there are burning cliffs of a different kind. Along parts of the Spanish and Portuguese coast, and in scattered places around the Mediterranean, geologists have found old sea cliffs streaked with red and black, the colors of rock that was once cooked from within. These are the scars of ancient cliff fires, some of which may have burned for centuries before going quiet. The exact ignition source for many of them remains debated. One idea is that pyrite weathering, much like in the smoking hills, did the work. A competing view points to bitumen, a thick, tar-like substance buried in some coastal rocks, which can smolder for long stretches once warmed. The truth may be different for different cliffs, and in many cases, the original spark is simply lost to time. What surprises researchers most is how stubborn these slow fires can be. A burning cliff does not behave like a campfire. There are no leaping flames, no roar, no obvious heart of the blaze. Heat hides inside the rock, Smoke seeps from cracks no wider than a finger. You can stand near a smoking hillside and feel almost nothing. Then place your hand on a stone and find it hot enough to startle you. The fire is everywhere and nowhere at once, threaded through the cliff like veins through a leaf. That hidden quality leads to another counterintuitive truth. The colder the climate, the longer some of these fires can survive. In the Arctic, the surrounding permafrost acts like a slow blanket, keeping the burning zone insulated and steady. Rain and snow cannot easily reach the hot pockets buried inside the rock. Even seawater splashing against the base of the cliff does little to cool the fire above. A flame that would die quickly in a wet forest can persist for ages inside a frozen coastline. How long can a self-feeding cliff fire really last? No one is sure. Some researchers believe the smoking hills could keep burning in one form or another for as long as the sea keeps eating into the shore and exposing fresh pyrite. Others suspect the fuel will eventually run thin, and the smoke will fade within a few more centuries. The cliff itself does not seem to care which answer is correct. It just keeps releasing its quiet white plumes into the Arctic wind, while the waves below carry small pieces of burnt stone out into the cold gray sea. Long before anyone knew what methane was, before geology had a name, before chemistry could explain why some stones gave off smoke, people gathered around flames that came out of the ground on their own. These flames have shaped human stories for thousands of years. They sit at the meeting point of fire and faith, of science and wonder, of the deep earth and the people who lived above it. Think of a small group of travelers in ancient times, walking across a dry plain in what is now the Middle East. The sun is setting. The land is bare. And then, in the distance, they see a soft orange glow rising from a crack in the rock. They walk closer. The flame is warm but small, steady but quiet, and it does not seem to feed on any wood. To them, this is not a chemical reaction. It is a message. It is a doorway. It is something to gather around, to name, to remember. That feeling has not really left us. Even today, standing near a vent of natural gas that lights itself on the wind, most most people feel a soft hush in the chest. The fire seems patient. It seems older than anything around it. And in many places, it truly is. The fire pits of the ancient world were not isolated curiosities. They were tied to the deeper systems of the planet. Some sat on top of slow leaks of methane rising from coal seams far below. Some sat above oil-rich rocks that had been cooking gently for millions of years. Some sat near faults where the crust had cracked just enough to let the breath of the deep earth reach the surface. Each flame was the visible tip of a hidden plumbing system, a quiet conversation between the buried past and the open sky. In ancient Persia, certain temples were built around natural gas flames that had burned, by some accounts, for centuries before anyone arrived. The priests did not light the fire. They tended it, sheltered it, kept the wind from twisting it sideways. The flame became sacred partly because it did not need them. It was already alive when they got there, and it would still be alive, they believed, long after they were gone. In other parts of the ancient world, similar flames became landmarks for travelers. Caravans found their way at night by the glow of burning gas seeps on lonely hillsides. Sailors steered toward small fires on rocky coasts, knowing that the flame meant safe harbor or a known shore. The earth, in a sense, was lighting its own road signs, and people learned to read them. What ties these scattered flames together is the same quiet engine. Deep below, organic matter from old forests, old oceans, old swamps slowly turns into gas. Pressure builds. Tiny pathways open. The gas rises. When it reaches the surface, it meets oxygen and sometimes a spark from lightning or a hot stone or a passing traveler with a torch. And then it burns. The flame is small, but the system feeding it is enormous. The fire on the rock is the visible end of a long underground story. The mystery is how long these stories last. Some ancient flames described in old texts are gone now. The gas ran out, or the cracks closed, or the wind found a different path. Other flames are still burning in the same spots their grandparents' grandparents knew. Why some persist and others fade is not fully understood. One idea is that the underground reservoir simply runs dry on on its own quiet schedule, and we cannot easily measure how full it is. Another idea is that small shifts in the rock far below slowly close the chimneys that let the gas escape. Both may be true in different places. We do not always know which is which. These ancient fire pits also remind us that the line between geology and human memory is thinner than it seems. A flame burning on a hillside is a piece of chemistry, yes, but it is also a piece of a story that has been told for 100 generations. The fire connects the deep rock to the open air, the prehistoric forest to the modern eye, the breath of the earth to the wonder of a watching mind. And so, on quiet nights, in places where the old flames still flicker, a person can stand near the warmth and feel the whole long chain at once. The buried plants, the slow gas, the patient crack, the steady glow, the story passed forward, everything playing together in a soft, low harmony with no clear beginning and no easy guess at the end. There is a kind of fire that no one lights. It begins on its own in the quiet folds of the world, where damp matter sits in slow conversation with the air. A pile of hay in a barn loft, a heap of coal at the edge of a mine, a mound of peat warming under a summer sun. Given the right mix of moisture, oxygen, and time, these humble piles can grow warm from within, and then warmer still, until they begin to glow. The science behind this slow ignition is reasonably well understood, yet still full of soft edges. Microbes feed on the damp material, releasing heat as they work. If the pile is large enough and packed just right, that heat has nowhere to escape. The temperature climbs, the microbes die off, and the chemistry shifts. Now the heat itself begins to drive new reactions. Plant oils break down. Coal dust reacts with the air. Somewhere deep inside the pile, the temperature crosses a quiet threshold, and a flame appears in the dark. Farmers have known about this for centuries. A barn that holds wet hay through a humid summer can smolder without warning. The outside looks calm and golden. The inside, hidden in the heart of the stack, may already be glowing a dull orange. Old farming books warned of this danger long before anyone knew the chemistry behind it. They simply noted that hay packed too damp would sometimes, on its own, decide to burn. Coal does something similar, only slower and stranger. Fresh coal exposed to air begins to react with oxygen at the surface of every tiny grain. The reaction is gentle at first, almost shy. But in a pile of crushed coal, or in a coal seam newly opened by mining, that gentle warming can build. One theory holds that most underground coal fires begin this way. A slow oxidation that never quite cools off, until one summer the seam simply lights itself. Another view emphasizes outside ignition, like lightning strikes, brush fires, or sparks from old mining equipment, as the true beginning of most blazes. The honest answer is that both happen, and in many cases, we cannot tell which came first. Peat is the strangest of all. It is partly decayed plant matter, soft and dark, lying in thick mats across northern bogs and tropical swamps. Dry peat is essentially fossil fuel in slow motion. In a hot, dry season, peat can begin to smolder on its own, especially where it has been drained or disturbed. The fire then sinks downward, eating through the layers, sometimes reaching depths of several meters. Above ground, there may be no flame at all, only a faint blue haze rising from the moss. What makes spontaneous combustion so haunting is its patience. A pile of organic matter can sit for weeks, months, even years, slowly warming, slowly drying itself from the inside before any sign appears at the surface. By the time a wisp of smoke curls up, the fire has often already taken hold in the heart of the pile. This is why some researchers think certain long-burning coal seams may have begun decades or centuries before anyone noticed them. The smoke we see today might be the late chapter of a fire that started during the time of our great-grandparents. The earth itself has likely been doing this for a very long time, long before humans arrived. Lightning, sunlight, and microbial heat were already coaxing flames out of dry grasslands, peat bogs, and exposed coal beds. The burning mountain of New South Wales is believed to have started this way, perhaps from a lightning strike, perhaps from a slow self-heating in the exposed seam. 6,000 years later, the fire continues, drifting along beneath the ridge at its own quiet pace. What remains unresolved is how often spontaneous combustion sets off the truly long-lived fires. Some scientists believe most eternal flames trace back to natural self-ignition, with human activity only adding new ones in the last few centuries. Others suggest that lightning, wildfire, and even ancient volcanic activity may be the more common spark, and that pure self-heating mainly produces small, short-lived fires. The records simply do not go back far enough to settle it. What we can say is that the world is always preparing itself in small ways to burn. In a peat bog at this very moment, microbes are warming a hidden pocket of damp moss. In a hillside seam, coal grains are quietly reacting with the air. Most of these warmings will fade. A few will not. Somewhere, perhaps tonight, a fire is being born without a match, without a witness, without a name, settling in for what may become a very long stay. There are places on Earth where fire takes the form of liquid, not flames flickering above coal, not gas hissing from a crack in the rock, but molten stone itself, glowing in the open air. These are lava lakes, and a small number of them have stayed lit for so long that no one alive remembers their birth. A lava lake is exactly what the name suggests. It is a pool of melted rock, held in the bowl of a volcano's crater, kept hot by a slow connection to the deeper plumbing of the earth. The surface looks like dark, wrinkled skin. It cools and crusts over as it meets the air, then cracks and splits, showing the bright orange beneath. The cracks shift and move, drawing slow patterns across the lake, like glowing veins on the back of some enormous sleeping creature. The light a lava lake gives off is unlike almost any other light on Earth. By day it can look strangely dim, a dull red beneath a haze of gas. But at night, it becomes its own small sun. The crater walls turn gold. The clouds above the volcano catch the glow and shine back down, painting the whole mountain in a soft amber light that can be seen from many miles away. Sailors and travelers used these glows as landmarks long before maps were reliable. A few of these lakes have been burning in some form for an astonishingly long time. The lava lake at Mount Erebus, in the cold quiet of Antarctica, has been active for decades and may have existed in some shape for far longer. The lake at Nyiragongo in Central Africa was first described by outside observers in the late 1800s, and the local people had known it for generations before that. Erta Ale in the hot desert lowlands of Ethiopia has held a lava lake for more than a century by the best estimates, and possibly much longer. The mystery is how a lava lake should not last. Molten rock loses heat quickly when it meets the air. The crust forms, traps some heat, but the lake should still cool and harden over time. Something must be feeding it from below. Something must be circulating fresh, hot material up into the bowl, while cooler, denser material sinks back down. One theory describes this as a slow convection loop. Hot rock rises through a narrow conduit, spreads across the lake, cools at the surface, and then sinks back down through the same passage, making room for the next pulse of heat. In this picture, the lake is the visible top of a tall, thin column of moving magma that reaches deep into the crust. Another view suggests that gas plays the larger role. Bubbles of dissolved gas rise through the magma, dragging hot material upward with them, almost like the motion inside a lava lamp. Both ideas may be partly right. Both still leave open questions about why some volcanoes hold lakes for centuries, while others, with seemingly similar plumbing, never form one at all. What the light reveals is a kind of breathing. Watch a lava lake long enough, and you see slow waves cross its surface. The crust shifts. A bright crack opens, widens, then closes again as a new skin forms. Sometimes a section of the cooled top sinks, pulled under by the colder, denser rock, and a fresh patch of brilliant orange appears in its place. The lake exhales gas in soft puffs. It glows brighter, then dimmer, then brighter again, on rhythms that no one fully understands. The colors shift with temperature. The hottest fresh lava can shine almost white yellow. As it cools, it slides through orange, then a deep red, then a dark brick color, and finally into the near black of fresh basalt rock. A single moment of looking at a lava lake holds all of these colors at once. scattered across its surface in a slow, shifting mosaic. The question of how long a particular lake can keep burning has no clean answer. Some have gone quiet for years and then returned, suggesting that the heat source below was never truly gone, only resting. Others have drained suddenly during eruptions, the entire glowing pool vanishing in hours, only to refill slowly over months. The lake is not a fixed object. It is a balance, held between heat from below and cold from above, and that balance can tip in either direction without much warning. For tonight, picture one of these lakes in the dark. The wrinkled skin, the soft orange veins, the slow breath of light against the crater walls. A fire that has been quietly burning since long before you were born and may keep burning long after, for reasons we still do not fully understand. There are old stories told in many parts of the world about small flames that drift just above the surface of marshes and bogs at night. The lights are pale, sometimes blue, sometimes green, sometimes a soft yellow. They hover, they move, they seem to wander across the wet ground as if guided by some quiet purpose. In English, they are called will-o'-the-wisps. In other languages, they carry other names, each one tied to old beliefs about lanterns held by unseen travelers. And tied to those lights, in nearly every story, are sounds. A faint hiss, a soft pop, a whisper of air moving where no wind should be. The sounds, when they are reported at all, are very quiet. People who have walked through marshes at night describe a kind of breathing in the reeds. A small ticking, almost like a clock made of water. A faint sigh when the flame appears, and another when it fades. These reports are old, and they are not always reliable. Memory in the dark can be a strange thing. Yet the stories repeat themselves across centuries and across continents, which makes them hard to dismiss entirely. The leading explanation is that will-o'-the-wisps are caused by gases rising from rotting plants in the bog. As leaves and roots break down beneath the wet ground, they release methane and other gases. Some researchers think a gas called phosphine mixed with diphosphane may ignite on contact with air. If that is true, the soft pop a witness might hear could be the moment of ignition. hiss could be the slow escape of gas through the muddy crust above. The flame would be small, cool, and quick to vanish. It would not roar. It would barely breathe. But this explanation is not settled. Laboratory experiments have struggled to reproduce a steady, drifting marsh light using only the gases found in bogs. Some efforts have made small flashes. Others have made nothing at all. The exact mix of gases, the right temperature, the right humidity, the right amount of dust or mineral in the air. None of these conditions are fully understood. So while the chemical theory is the most accepted, its details remain open. Other ideas have been offered over the years. One theory suggests that the lights are a kind of cold luminescence caused by certain microbes or fungi that glow softly in damp ground. This would explain why the lights do not always feel warm to those who claim to have stood near them. It would also explain the strange silence some witnesses describe, broken only by the small ticking sounds of insects and water. But cold luminescence is usually steady, not drifting. So this theory does not quite fit either. A third idea points to small electrical effects in the marsh. Decaying matter, mineral-rich water, and rising gases might together create faint pockets of static charge. Under the right conditions, these pockets could glow briefly and release a tiny crackle. Some researchers have wondered whether the soft hiss in old reports is the sound of these quiet electrical discharges. Others doubt that a bog could ever build enough charge to do this. The debate is gentle and ongoing. What links all these ideas is the sound, or really the near absence of it. Will-o'-the-wisps are not loud fires. They are not the deep roar of a burning mountain, or the long whisper of a coal seam beneath a town. They are small, soft, fleeting. If they make a sound at all, it is the sound of something just barely happening. A breath, a tick, a faint sigh on the surface of black water. Sound, in the world of slow-burning earth, often arrives at the edge of hearing. A coal fire deep underground may travel for years without any audible voice at all, betrayed only by the warmth of stones in winter. A methane seep may bubble so softly that you must lower your ear to the puddle to hear it. The bog light, if it is real, belongs in this same quiet family. It is a fire so small it almost does not deserve the name. And yet people keep reporting them. In Ireland, in Japan, in the swamps of the American South, in the wet forests of Central Europe, in the peatlands of Scandinavia, the lights and their quiet sounds remain part of human memory. Even though the science is incomplete, we are still not sure what we are listening to when we hear that faint pop in the reeds. We are still not sure what is rising from the ground when the pale flame appears. The mystery of the will-o'-the-wisp is small, but like all small mysteries on Earth, it sits patiently, waiting to be understood, while the night listens with it. There is a quiet kind of math woven through the burning places of Earth. It is not the math of textbooks or chalkboards. It is the math of slow chemistry, of long arithmetic carried out by stone and gas and time. When an oil field catches fire, the numbers it whispers are surprisingly elegant. Each drop of crude carries within it a fixed amount of stored sunlight, gathered slowly from ancient seas, and the flame above it is simply that sunlight returning to the sky. Consider the strange balance that lets such a fire continue. For a flame to live, it needs fuel, oxygen, and heat in steady ratio. Too much fuel, and the fire smothers itself. Too little, and it dies of hunger. The burning oil seeps and gas fields of the world sit in a narrow band of just right conditions, where the leak from below matches the air from above with quiet precision. This balance, repeated across centuries, is the hidden equation behind every long-lived flame. In the deserts of the Middle East, certain oil fields have flared their excess gas for many decades. The plumes rise in tall orange columns, visible from far above the clouds. Each column represents a simple calculation. So many cubic meters of gas per minute, so much oxygen drawn from the surrounding air, so much carbon and water vapor sent skyward. The numbers are not mysterious in themselves. What is mysterious is how long these reservoirs can keep feeding the flame. Geologists have tried to measure this. They study the porous rock below, the slow movement of hydrocarbons through cracks and pockets, the pressure that pushes them upward. From these measurements, they build models, gentle estimates of how much fuel remains. One model might suggest a seep will burn for 50 more years. Another, using slightly different assumptions, might suggest 500. The truth lives somewhere in that wide, soft space between guesses. The Kuwaiti oil fires of the early 1990s offered a strange, natural experiment. Hundreds of wells burned at once, releasing enormous quantities of stored carbon into the sky. The smoke darkened the desert for months. Engineers eventually capped each well, one at a time, in a slow and patient process. Yet even now, researchers are still studying the long shadows those fires cast on the soil, the air, the rainfall patterns of the region. The math of what was released continues to be calculated decades later. There is a softer arithmetic at work in smaller, quieter places. A natural gas seep in a remote valley may release only a trickle of methane each hour. The flame above it might be no larger than a candle. Yet if that trickle has continued steadily for 1,000 years, the total fuel consumed becomes a number too large to picture easily. A small flame, multiplied by deep time, becomes a vast, slow burning. This is the elegant pattern that runs through all of Earth's eternal fires. They are rarely dramatic in any single moment. Their power lies in patience, in the multiplication of small things across long stretches of time. A coal seam fire that creeps forward by only a few meters each year will, over a century, travel the length of a small town. A gas seep that releases the breath of a sleeping animal each minute will, over millennia, exhale a small ocean of vapor into the sky. The numbers are beautiful, but they are also uncertain. We do not always know how deep a reservoir runs, or how connected it is to others nearby. A flame that seems isolated on the surface may be drinking from a network of underground pockets we have not yet mapped. One theory holds that many of the world's eternal flames share hidden plumbing, fed by the same slow rise of gas from deep rock. Another suggests each is its own small system, sealed off from its neighbors by layers of clay and stone. The evidence supports a little of each in different places for different reasons. What stays constant is the quiet elegance of the underlying rule. fuel plus air plus heat, balanced just so, equals flame. Change any one of the three, and the equation collapses. Yet, across the surface of our planet, in dozens of strange and scattered locations, the equation has held for centuries, sometimes for millennia, sometimes for spans of time so long that no human record exists of the flame's beginning. There is comfort in this slow mathematics. The world is not chaotic in its burning places. It is patient, ordered, following rules so simple that a child could understand them, and yet so deeply unresolved in their long-term outcomes that the brightest scientists cannot say with certainty when any of these fires will finally rest. Step away from the great burning fields for a moment, away from the oil fires and the deep coal seams, and walk instead into a quieter place. Picture a low, flat wetland in the cool half of the world. The ground is soft and dark. Moss grows in thick green and rust-colored mats. Pools of still water reflect a gray sky. The air smells faintly of old leaves and something sharper, a hint of swamp gas. This is a peat bog, one of the gentlest landscapes on Earth, and one of the most delicately balanced. Bogs hold a quiet kind of fire potential. Below the wet surface, layer upon layer of dead plants press down on each other. Over thousands of years, they turn into peat, a soft, brown, spongy fuel made mostly of half-rotted moss. When the bog stays wet, none of this burns. The water holds the carbon in place. The cold slows everything down. The moss keeps growing on top, while the old layers sink and compress beneath. In some bogs, on still nights, watchers have reported a soft glow drifting just above the surface, pale blue or greenish, or the color of a candle seen through fog. The glow moves slowly. It rises and falls. It does not roar or crackle. One idea is that pockets of methane and other swamp gases sometimes escape from the peat and ignite in tiny, near-invisible flames. Another idea is that the glow is not flame at all, but a cold light produced by bacteria or fungi living in the wet ground. The question has never been fully settled. Different bogs may glow for different reasons. Some glows may not even exist outside the imagination of tired travelers. Others may be real, brief, and almost impossible to study. The balance that keeps these places quiet is astonishingly thin. A bog burns or does not burn depending on a few inches of water. Lower the water table by even a small amount, and the upper layers of peat begin to dry. Dry peat is a slow, stubborn fuel. Once it catches, it can smolder underground for months or for years, much like the coal fires in earlier chapters. The same wetland that gently glows on a summer night could, in a drier season, hold a fire that no one knows how to put out. This is part of what makes Earth's burning places so strange to think about as you drift toward sleep. The line between calm and slow disaster is sometimes only a season of rainfall. The same gases that flicker harmlessly above a marsh can build up in a closed space and ignite with force. The same peat that stores carbon for 10,000 years can release it in a slow underground burn. The bog is both fireproof and flammable. Depending on conditions we can barely measure from the outside. Step further back, and the balance grows even more remarkable. Earth sits at a distance from the sun, where water can be liquid, frozen, and vapor all at once. Its atmosphere is thin compared to the size of the planet, a fragile shell of mostly nitrogen and oxygen. That oxygen is what allows fire to exist at all. Too little of it, and flames cannot survive. Too much, and even damp wood would burn easily. The amount we have sits in a narrow zone where forests can grow, candles can flicker, and bog gases can produce only a soft, occasional glow rather than a runaway blaze. Researchers who study peatlands often speak of them with a kind of quiet respect. A healthy bog is a slow machine for storing carbon and water. It cools the air above it. It feeds streams. It hides ancient pollen, ancient tools, sometimes ancient bodies preserved in the tannin-rich water. And it holds, in its lower layers, the memory of every plant that has ever grown there. All of this depends on the bog staying wet. How long could a peat fire feed itself if conditions shifted? In some northern bogs, fires sparked by lightning have burned through entire summers, going to sleep under winter snow and waking again in spring. Whether such fires could, in theory, keep burning for many decades remains an open question. The fuel is there. The oxygen is there. Only the water stands between a glowing wetland and a long, quiet burn. Imagine then the bog at night. A pale mist hangs low. The moss is cool to the touch. Somewhere out in the dark, a faint blue light rises, hovers, and fades. No one is certain what it is. The ground holds its breath. The balance holds, and the soft glow drifts on, gentle as a thought, over a fuel that has waited 10,000 years for a question no one has yet answered. Beneath certain places on Earth, whole networks of fire move through the rock like slow rivers of heat. They are not single flames in single rooms. They are sprawling underground cities of smolder, branching and turning through coal seams and peat beds, eating their way along buried fuel for years, for decades, sometimes for centuries. We can map their edges. We can measure the warmth that leaks up through the soil. We can sniff the gases rising from cracks. And yet, when scientists try to describe what is truly happening down there in the dark, they often have to admit that much of it remains hidden from view. The Chimaera coalfield in eastern India is one of the largest of these hidden cities. Fires there have been burning since at least 1916, and possibly longer. They creep through layered seams of coal that lie close to the surface in some places and deep below the ground in others. Hot patches of earth glow faintly at night. Steam rises from cracks in the soil. From above, the fields look ordinary by day, but thermal cameras show a glowing web of heat, branching like the roots of some enormous, slow tree. No one knows exactly how many separate fire fronts are active. Estimates vary widely, and the numbers shift as the fires move, merge, and divide. What makes these underground cities so difficult to understand is that we cannot easily look inside them. A surface fire is visible. A coal seam fire is not. Researchers must guess at its shape using indirect clues. They drill boreholes and lower thermometers. They measure the gases at the surface. They use satellites to track tiny changes in heat radiating from the ground. From all this evidence, they build models of what the fire might look like in 3 dimensions. But the models disagree with each other, and the fires themselves do not hold still. A passage that was burning last year may be cold now. A cold seam nearby may have caught light without warning. One open question is how these fires choose their paths. Coal seams are not uniform. They contain layers of harder and softer material, pockets of gas, veins of moisture, faults and fractures that may or may not let oxygen through. Some researchers believe the fires follow the path of easiest airflow, creeping toward whatever cracks deliver fresh oxygen from above. Others suggest the fires are shaped more by the quality of the coal itself, lingering where the fuel is richest and slowing where it is poor. Both ideas have evidence behind them. Neither fully explains the strange, looping shapes that some underground fires take, doubling back on themselves as if guided by something we have not yet identified. There is also the question of how deep these fires can go. In Geria, in Centralia, in the burning fields of China and Indonesia, most active fires sit within a few hundred meters of the surface. Below that, the oxygen thins out and the pressure grows. Some scientists think this sets a natural ceiling on how deep a self-sustaining coal fire can travel. Others wonder if narrow chimneys of airflow might let fires reach surprising depths along faults and old mine shafts. The deeper a fire burns, the harder it is to detect, and the harder it is to study. Whole branches of these underground cities may be hidden from us simply because we have no good way to see them. Then there is the deeper puzzle of how to stop them. Crews have tried flooding fires with water, sealing surface cracks with clay, digging vast trenches to cut off the fuel ahead of the burn. Sometimes these methods slow the fire. Sometimes they push it sideways into unburned coal. Sometimes the fire simply waits, smoldering quietly, and then springs back to life once the crews are gone. There is no reliable recipe for extinguishing a large underground fire. Each one seems to require its own approach, and even then the outcome is uncertain. What lives inside these hot zones is another quiet mystery. Some bacteria seem to tolerate the warm, gas-rich soils above coal fires. Some plants do not. The chemistry of the ground changes as the fire passes, leaving baked clay, melted minerals, and strange crusts behind. Whether new ecosystems form in these warmed corridors, and how long they last after the fire moves on, remains poorly studied. For now, we know that these underground cities of slow fire exist. We know roughly where they are. We can listen to them breathe through their vents and feel their warmth in the soil. The deeper map, the one that shows every chamber and every glowing tunnel, is still mostly blank. In the flat desert of Turkmenistan, a wide pit glows in the dark. The locals call it the door to hell. For more than 50 years, this crater has burned without rest. The flames lick the rim of the hole, soft orange in some places, deep yellow in others. At night, you can see the glow from many miles away. The sand around the pit holds a steady warmth, and the air above shimmers like heat above a stove. The story goes that a drilling crew opened the ground here in the early 1970s. The earth gave way beneath them, swallowing their equipment into a wide pit. Gas began to leak out in great quantities. Worried about the danger to nearby villages, someone made a choice. They set the gas on fire. The thinking was simple. Let it burn off in a few weeks, and then the land would be safe again. No one expected the flame to still be there half a century later. That single decision turned a small accident into one of the most famous fires on Earth. The gas below has kept coming. The flame has kept feeding, and no one knows how long it will last. This brings us to the question of the future. What happens to a place like this over a very long stretch of time? Over 1,000 years? Over 1,000,000? Over 1,000,000,000? The Earth we know now will not be the Earth we have then. Continents will drift into new shapes. Oceans will open and close. Mountains will rise where deserts now lie. The very ground that holds the door to hell will move very slowly across the face of the planet. In 1,000,000 years, the Karakum Desert may not be a desert at all. The climate could shift many times. Rain may fall here. Forests may grow. Or it could become drier still, a place of bare rock and salt. The crater itself, if no one tends to it, will likely change in ways we cannot predict. The walls may crumble. The pit may collapse on itself. The gas pocket below may empty, or it may find new paths to the surface. There are at least two ways to think about its future. One idea is that the fire will simply run out. Gas pockets are not endless. Once the supply below the crater drains away, the flame will flicker, shrink, and finally go dark. Some who study these things believe this could happen within decades. The pit would then become a quiet hole in the sand, slowly filling with dust and time. A different view holds that the gas field is much larger than we know. Deep below the surface, methane may keep moving up through the rock for centuries to come. In that case, the flame could outlive every person alive today, and their grandchildren, and theirs as well. Which view is correct, we cannot say with certainty. The geology below is hidden from easy study. We only see what comes to the surface. Then think further out. In 100 million years, the plates of the earth will have moved many hundreds of miles. The patch of crust beneath Central Asia may have shifted, folded, or sunk. The pit will be long gone, ground down into ordinary sediment. The gas, if any remains, will have escaped or been trapped in new pockets far below. In 1 billion years, our planet itself will look strange to us. The sun will burn hotter and brighter, slowly drying the oceans. New land will form. Old land will sink. The story of a single burning crater in a single desert will be one tiny line in a very long book. Whatever flame we lit on purpose will have been forgotten by the rocks themselves. There is something humbling in that thought. We made a small fire by accident, and it became a wonder of the modern world. Yet, against the slow clock of the earth, even this long-burning flame is brief. The planet keeps going. New fires will start in places we cannot yet imagine. Old ones will fade without notice. What is most uncertain is whether anyone will be around to remember. Will future people care about a glowing pit in an old desert? Will they study it the way we study ancient fire pits today? Or will the door to hell pass into legend, half remembered, half invented, the way so many old fires already have? We do not know. The flame still burns tonight, steady and patient, throwing its soft light against the rim of the pit. It does not know about the future. It only knows the gas, the air, and the slow rising heat from somewhere deep below. Step back for a moment, all the way back, and consider what a flame really is. A flame is not a thing. It is an event. It is a slow handshake between fuel and air, a quiet meeting of molecules that releases the warmth they were holding. When you look at one of these long-burning places, you are not looking at an object. You are looking at a process that has simply not finished yet. Most fires we know are brief. A candle burns for hours. A campfire burns for a night. A forest fire, even a vast one, runs its course in days or weeks. The fires we have sat with in this episode are different. They have outlasted empires. They have watched generations of humans come and go above them, while they quietly continued their slow work below. To last that long, a flame needs three things at once. It needs fuel that does not run out. It needs air that keeps arriving. And it needs a temperature that stays high enough to keep the reaction going. Take away any one of these, and the fire ends. Why these three things keep finding each other for hundreds or thousands of years in certain places is part of what still puzzles researchers. Some of the answer lies in geology. The Earth has been storing fuel inside itself for hundreds of millions of years. Coal seams, oil pockets, pockets of natural gas, layers of peat, beds of oil shale. These are the slow gifts of ancient swamps and ancient seas, pressed down and cooked by time. When a crack opens to the surface, the fuel finally meets the air it has been waiting for. The handshake begins. But fuel alone is not enough. A coal seam buried deep underground can sit untouched for ages. Something has to ignite it. Lightning, a wildfire above, a spark from human hands. Even the slow heating of certain minerals as they react with water and oxygen. Once lit, the seam may smolder for a generation, or it may flare briefly and die. Why one seam keeps burning while another goes dark just a few miles away is not always clear. The air is the other half of the mystery. Underground fires need oxygen, and oxygen has to find its way down through cracks, through old mine shafts, through the spaces between grains of rock. If the air arrives too slowly, the fire suffocates. If it arrives too quickly, the fire burns out its fuel in a rush. The fires that last for centuries seem to have found a strange middle path, a slow breath through stone that keeps them alive but never lets them race. Step further back still. The carbon in that burning coal was once a tree fern in a carboniferous swamp, drinking sunlight that fell on Earth 300 million years ago. That sunlight came from a star 8 light minutes away. The carbon atom itself was forged inside an older star long before our sun was born, and scattered into space when that star died. It drifted through the dark for a long time. It settled into a young planet. It became a leaf. The leaf fell into a swamp. The swamp became coal. The coal began to burn. When you stand near one of these eternal flames, you are watching ancient starlight being released slowly into the night air. The warmth on your face is the warmth, a carboniferous afternoon stored away for safekeeping. The flame is simply giving it back. We are part of the same story. The calcium in your bones, the iron in your blood, the carbon in every breath you take. All of it was made inside stars and folded into Earth long before there was anyone here to wonder about it. The same atoms that feed a long-burning seam in Pennsylvania, or a quiet fire behind a waterfall in New York, have moved through countless other forms. They have been ocean and stone and seed and creature. Tonight, some of them are flame. Tomorrow, they will be something else. And the question that began this episode is still open. We do not know exactly why some fires last 1,000 years and others 1,000 minutes. We do not know how long the longest of them will continue. We do not always know how to stop them, or even whether we should. The earth keeps its slow secrets, and the flames keep burning, and the night air carries their warm breath upward toward the stars they came from. It is a strange and gentle thought to rest with. Everything is borrowed. Everything is connected. Even fire is just matter remembering, for a little while, what it once was. And so, we come to the quiet end of our long sitting by the fire. We've wandered from a hillside in Australia that has smoldered for 6,000 years to a flaming pit in the deserts of Turkmenistan, to a small, steady flame behind a curtain of falling water in the woods of New York. We've stood in our imagination on the warm ground above the buried coal fires of Pennsylvania, of India, of China. We've watched soft blue lights drift across northern bogs, and we've thought about the lava lakes that have glowed inside their mountain throats for longer than anyone can remember. Through all of it, the same gentle question has stayed with us. Why does Earth keep certain fires alive for so long? How can a flame feed itself for 100 years, 1,000 years, perhaps more? We've heard partial answers. Slow seeps of methane, buried beds of coal with just enough air to glow, heat that builds in the dark and finds its own quiet way to the surface. But we've also heard again and again that the full picture is not yet ours. The chemistry is known in pieces. The endings are not. No one can say with certainty when the door to hell will close, or when the last ember beneath Centralia will cool, or how long Yanarta's has truly been burning before anyone first wrote it down. That uncertainty is not a problem to solve tonight. It is simply something to rest beside, the way travelers used to rest beside a small fire in the open country, watching the coals shift and listening to the soft sound of the world breathing around them. Picture the earth now from a calm and quiet distance. A blue and white sphere turning slowly in the dark. On its night side, here and there, the faintest pinpricks of warm orange light. A flame on a Turkish hillside. A flame behind a waterfall. A glowing crater in a flat desert. A soft orange seam across a coalfield, each one tiny against the great curve of the planet, each one tended by nothing but the patient chemistry of rock and gas and time. Above them, the clouds drift in their slow white rivers. Below them, the deep ocean rests, dark and still, holding more water than the mind can easily picture. Mountains stand in their long silence. Forests breathe out their cool night air. Deserts cool from the day's warmth, the sand giving back its heat to the open sky. Glaciers hold their old blue light. Everywhere, the planet is doing its quiet work, without hurry, without fuss, without needing to be watched. And the fires keep their own time. They don't ask for attention. They don't compete with the stars. They simply burn soft and steady, the way they have burned through long centuries of human history. people have come and gone around them. Languages have changed. Cities have risen and fallen. The flames have just kept doing what flames do, fed by something deep and patient beneath the ground. There is something gentle in knowing that. The earth does not need us to understand it in order to keep going. The mysteries we leave unsolved tonight will still be here tomorrow, and the night after, and 100 years from now, waiting to be wondered about by someone else lying in the dark, listening to a quiet voice tell a long, slow story. You are one of those listeners now, held by a small warm room or a soft bed or the quiet hum of the night around you. Below you, somewhere down through the floor and the soil and the deep rock, the earth keeps its old heat. Far across the curve of the world, a small flame is dancing on a hillside that no one is watching. The wind is moving over it gently. The stars above it are turning in their slow circle, and the fire, as it has done for as long as anyone can remember, just keeps burning. Let your breath go soft. Let your shoulders settle. The mysteries are safe where they are. The flames will look after themselves. The planet will keep turning whether we sleep or not. And tonight, for a little while, it is your turn to rest. We may learn one day exactly why these places burn so long, or we may not. Either way, the wondering is its own kind of warmth. For now, that is enough. The fire is low. The night is wide, and you are exactly where you need to be. Subscribe for a brand new Earth topic every night. One tap, and something wonderful is waiting for you tomorrow. Sweet dreams.